Hi. Today I will show you visually concurrency in Go, but before I start, let me ask you one question. How do you mentally see the numbers from 1 to 100? Which image automatically appears in your mind when you think about them? It turns out that almost every person has its own internal representation of numbers, and this phenomenon even has its own name. It's called numbers forms. Here you may see the number forms from the real people. They were studied like many years ago, and you may be surprised how they strange and peculiar, but most importantly, how they are different. The concept of numbers is still the same for all us, but our internal representation, visual representation, is different. And I bet that your internal number form is quite different from the people sitting next to you. But it's not only about numbers. It also applies to many other abstract concepts like alphabet or days of week or time representation. For example, some people see a full year as a circle with a January at the bottom, going counterclockwise. And I, for example, I see it as a square with sides representing the seasons, with winter on the top and summer at the bottom. And some people even seeing them, the month in 3D, like around themselves, like in augmented reality. It's all cool, but the point here is that we heavily use our visualization power to understand and to represent abstract concepts. And concurrency is not an exception here. So one day I was preparing to the local Go meetup, and I was looking for the way to express my visual understanding of Go concurrency and share it with other people. Unfortunately, it was an easy task to do. We still lack of good tools for creating and sharing visualizations. And it's actually a big problem for education and for communication in general, because if you think about it, we have this huge visual cortex thing in our head that allows us to consume visual information at very high speed and quickly build complex mental models. Think about your children learning about solar system simply by looking to the fancy 3D animation and getting it in a second. But in order to send this visual model from your brain to someone else's head, we have to use these low-rate channels like words. So in terms of communication, we have pretty good input and pretty bad visual output. We kind of I/O bound here. So that was the problem. I ended up creating my own tool that will render this visualization for me and allows me to share with other people using the WebGL technology. And today I want to use this tool to explore some basics of concurrency in Go and common concurrency patterns. So let's go. At this point, I assume you're all here familiar with Go concurrency, so I will skip this typical introductory stuff, and let's go directly to the code. This is the super simple example, hello concurrent world. It has one anonymous Go routine, one unbuffered channel, one read, and one write. This is how I see it. What you see here is a time going downwards. This vertical line, let me repeat, vertical line represents the Go routine going through the time. Wide horizontal line is simply the connection between the Go routines. This just connect parent and a child. And this horizontal line, this blue horizontal lines, represent the sending value through the channel. And here's the tricky part, because there is no such action as sending value through the channel under the hood. There is pretty complex machinery happening here, but we can think about it using the mental concepts from the real world, like sending something through the pipe, or throwing the ball to the player, or giving the task to the worker. And for me, this is most important and the best part of the Go concurrency model. So the next example is the timer, which is slightly modified hello world example, just multiple 24 times. Don't be confused by function tick. It's just a function. It's not a concurrency entity. You will not see it in the visualization, but you will see this anonymous Go routine, channel, and sending over the channel. So let's see. Here you may see the main goroutine that spawns many goroutines. And I forgot to mention about the colors. I can highlight colors here. So the red color represents the blocked state. When the goroutine is blocked either by reading or sending to the unbuffered channel or by mutex or whatever, it is red. Red, it's not like bad. It's OK, but I just had to choose some colors. And the green color means unblocked state. So goroutine here is sleeping, actually, in this particular example. There is also a yellow color that means that goroutine heavily use CPU, but it's not the case here. So let's go next. Next example is the ping-pong, which is super brilliant example. It's super simple, but brilliant. So take a moment to digest the code. We have table here as a channel of integers, and the ball variable, which value means the number of hits. And two players that all they do is taking ball from the table, sleeping, increasing the hit counter, and sending it back. And it has pretty interesting visualization. So this is how I see it. No, sorry, wrong slide. This one. OK, so let me rerun. You may see how this ball passing between the players, how the value increased, how the goroutines get blocked and then sleep, get unblocked. But what I like most about this example is that we can easily get more players simply by invoking one more goroutine. So it's the same code, just 3 players. Again, we can see that every player has the same amount of time spent in blocked state and in sleeping state. And at this point, you may ask why there is so strict order. Maybe the next player that receives the ball should be chosen pseudo-randomly. But maybe it is pseudo-random. Maybe we're just lucky. So let's start 100 goroutines, or just for the sake of more clear visualization, 36. Oops. Yeah. So yes, we see the strict order. And the reason for that is that internally, reading from the Go channel implemented using the FIFO queue, first in, first out. So the first goroutine who asks for reading from the channel receives it first. But it's just an internal implementation. Do not rely on it. It can change in the future. But anyway, it's nice to be able to understand why we see what we see. Well, what else can we see here? Let's analyze the blocked state. We see that players mostly in blocked state, so it's not very efficient game to play the ping-pong with this number of players. So now let's talk a little bit about messaging patterns. The word pattern here doesn't mean anything like we used to use this word in object-oriented programming languages. It's just something that naturally emerged from the problem domain we're typically working on. And as Go concurrency heavily based on messaging, the messaging patterns is something natural. The first common pattern is the fan-in. It's basically the collection pattern when you have more producers and less consumers, typically one consumer. It's like aggregation of data. So in this example, we have 2 goroutines that produce some data sent via the channel at different rate, and one consumer, which is reader. So let's see. Yeah, let me rerun it so you see only the producers. You see how they send a different rate, but the reader receives all of them. They converge in this point. And so, yeah, this is actually an aggregation pattern. The next pattern, which is not really messaging, but it's kind of concurrency pattern, very common in Go, is the servers. When we use a lot of, we write a lot of networking software in Go, right? So it's a common thing to spawn one goroutine for each incoming network connection. So if you run this program and send some traffic on it, you will see this. And the reason why you don't see here any goroutines is because they are so short-lived, the response time is so fast that we just can't see them at this scale. And it's another great thing about having the visualization, because we can see the real timescales of events. And sometimes we don't feel it like intuitively in this scale. It's nanosecond scale. But let's add some messaging here. It's the same code, just we added one goroutine, let's say logger. It's a contrived example, but let it be logger, which reads from channel, and the handler on each connection sends the value to the channel. Here we go. Now we see the same servers pattern, which on every connection sends the value to the logger goroutine. And you may recognize already familiar fan-in pattern. It's just many values converging in one point. And also, we can guess that at some point, the logger goroutine will be like bottleneck here. Next pattern is the opposite of fan-in, is the fan-out. It's an opposite, when you have one producer and multiple consumers. Typically, we use this pattern when we want to redistribute our workload between anything, like network nodes or CPU cores, in this case, the CPU cores. And they're very trivial to implement in Go. And this pattern has another name, workers. So let's see how it looks like. You see the main goroutine, which is usually we call pool of workers, and the workers that grouped around this pool, and the tasks distributed evenly between them. But what I like most about this example, that it has physical meaning. We usually associate thickness of something with the power, right? And here, when I use workers pattern, I usually want my thread of execution to be more powerful. And here, it's like implementing of this association. My thread just get bigger, more powerful. But let's return, and the workers can contain the sub-workers or even more sub-workers if there is sense to do this. It's just a pattern. There are many implementations. OK, so let's return to the server with logger. And here we just applied the workers pattern to make our logger a little bit more powerful. So now it's not the bottleneck. And in this example, you can see that already all familiar patterns: the servers, the fan-in, and the fan-out. And for me, this is the best part of having good mental visualizations, is that you can combine those things very easily, and you can understand the code mentally much, much easier. Another interesting thing I want to talk about is the concurrent algorithms. But unfortunately, I haven't found like a lot of good concurrent algorithms. But this one is very interesting. I hope many of you already saw it. Take a moment to read the code. It's quite simple, especially if you know this algorithm before. It's ancient algorithm for seeking the prime numbers. But it's not, for me, it wasn't easy to digest this code very quickly, because here is what is happening. This is renaming of the channel on each iteration. And when I tried to understand this code on the first time, it was kind of confusing for me. So that's the visualization of the algorithm. And for me, it was the first time when I used this tool to actually understand the algorithm. Because all previous cases, I was using it just to confirm, it renders something like I see it. But in this case, it really helped me to understand. I can see the generate goroutine that sends the value. Then it sends to the filter, and filtering the numbers. And you can see here that the numbers that being sent to the main goroutine, they are prime numbers. Feel free to play with this example when slides are online. OK, what next? The GOMAX procs. The GOMAX procs value that sets how many CPU cores your program uses. We can try it with the workers pattern. Here we have 24 workers. And in this particular case, the worker's actually doing something, some heavy computation. So let me highlight this yellow color. Do you remember I said that yellow color means doing some real computation, some mathematical computations. And you see that it's like very small fraction of time. And mostly GoRoutines spend here time in just being blocked. And it makes sense that, let me rerun it, it's just one core and 24 concurrent workers. So now the same code with GOMAX procs equal 24. It actually runs much, much faster. The time scale doesn't show it. But you can see here that most of the time GoRoutines spend here in doing actual work using CPU, and only a fraction of it in the blocked state. So this is cool. And next, I want to visualize is the GoRoutines leak. It's a scary thing, actually. It can happen if you, for example, create an object and it starts the GoRoutine in the constructor function, and the object goes out of scope, but the GoRoutine is still running. And I see it something like this. It just infinitely launching more and more GoRoutines. And it kind of, actually here it kind of looks beautiful, but it shouldn't be. It should be like with pain and blood and screams and explosions, because it's a ticking bomb for your program. It will crash anyway, so be careful with that. OK, a couple of words about the tool itself. Right now, it's based on the Go execution tracer, which is built-in tool in Go since Go 1.5. And I think it's very undervalued tool at this moment because it's very powerful. It gives very, very deep insight on what is happening under the hood. But it's probably undervalued because it's really hard even for us, for developers, even hard to understand what we can get from this data because it just traces, it's binary data. And we probably need more visual approaches to this, to analyzing, maybe the data science approach, to analyze this trace and understand what we can get from it. So I encourage you to take a look on the Go tool trace, especially because in Go 1.7 it will become even more cooler, even more performant. So my tool, actually, what it does, it takes the trace. It can rewrite your code, add this tracing possibility for you. It collects the trace, it analyzes it, correlate events. Remember, I told that there is no such event as sending values. At least there are two events, reading and sending, and we need a way to correlate it. And then starts the WebGL, the server with WebGL code. So this tool will be open source today by this link. It still requires some small patch to go. It's trivial to add, and you, of course, can use the pre-made Docker images. The thing is, I had to add some 2 events and some correlation logic. And right now, this tool is like more for educational purposes, for the examples like this. Because if you run it on a really huge program, and the trace will be so complex that WebGL will crash your browser. Maybe I will overcome it in some time. Let's see. OK, and as a final note, I want to make small tribute to this video, which is I recommend every time when someone asks me something to read or watch about the understanding Go concurrency. And this video builds like solid understanding what concurrency is and what concurrency isn't. So 2 questions. What is parallelism and what is concurrency? Now let's try to visualize it. So parallelism is simply running a bunch of things in parallel. There is no structure. It can have different forms, but it just executing things in parallel. And concurrency, it's the way of structuring your program. So this is concurrency. And this. And this. And all that concurrency. Thank you.